Hello, I am today going to talk about virtuality and reality, the simulation, replication, distinction, and its implications for AI. What I'm mainly going to focus on is so-called neuromorphic, that is brain-like hardware. And the question I want to ask is, how likely is it for neuromorphic computers to develop artificial consciousness when compared to standard digital computers? Well, first of all, why does that even matter? Why care about consciousness? Why would that be important to us? Well, the answer to that question is quite simple. Consciousness is more or less widely considered to be somehow the basis of morality. And if we want to know whether a certain artificial agent, be it advanced AI systems or robots or whatever, need to be granted moral status, we have to know whether they are conscious or whether they are dead objects. Also, Thomas Metzinger, for example, wants to assess the risk of what he calls suffering explosion. He considers the risk of the researchers by chance and unknowingly creating artificial systems that are at least minimally conscious and therefore are capable of suffering. And he urges research community and the politics to slow down on the process of artificial consciousness, on AI development, until we have better understanding of what we are doing there. How high are the chances of creating artificial consciousness? While there's quite some debate, or actually a huge debate on consciousness and digital computers, neuromorphic computers so far have been disregarded by philosophers. Nobody has actually ever talked about them, and I find that quite surprising since we know the brain to be conscious, and brain-like computers are at least similar to brains, so why not ask the question, could they become conscious as well? And I think that question is quite urgent since there already are neuromorphic systems. For example, the so-called Spinnaker 2 system, currently under development in Dresden, which actually already have the size of a mouse brain. And since we know mice to be conscious, we really should take a look at those systems and consider whether they might be conscious or might become conscious in the future as well. First of all, what is neuromorphic hardware? Neuromorphic hardware mimics the structure of the human brain, utilizing interconnected artificial neurons to process information. So on neuromorphic chips, there are actually artificial neurons wired together and are interconnected and put on one chip. Those systems are designed to perform tasks with low power consumption. That's actually why they are developed. And they depart from the traditional von Neumann architecture in several ways. The von Neumann architecture is the way traditional computers, like your laptop, my laptop, are built. And neuromorphic hardware works entirely different, using actual physical neurons, actual physical synapses, which interconnect them. And they are already not just some research projects, but market-ready chips by Intel, IBM, and others. Here on the lower right, you can see the so-called Intel Loihi 2 processor, which you could actually already go out and buy. The main thesis I want to be defending in this talk is that AI algorithms running on neuromorphic, that is brain-like hardware, are more likely to generate artificial consciousness than simulations on standard digital hardware. That's what I want to be defending. And you might ask, well, why would that be? Just in a couple of slides, I'm going to present you an argument. And in order to understand that argument, we need some concepts first. So the first concept would be that of a scientific model. What is a scientific model? A scientific model is a mathematical structure together with an interpretation. For example, here on this slide you can see the so-called Lotka-Volterra predator-prey model. I think most of you have heard of it in some way or another. It predicts the population density of predator and prey, for example, of foxes and rabbits. And it uses those differential equations here on the right to describe and to predict its behavior. And what we get is these oscillations in the predator and prey population. Okay, and how is this a model? As I already mentioned, we have a mathematical structure. Here on the right, this is the differential equation. And the model gives more than that. It actually says what that differential equation describes. How is the mathematical structure connected to the real world? And in the case of the Lotka-Volterra model, the X stands for the prey population and the Y represents the fox population. That's how the symbols are connected to the real world. So now let's talk about what are simulations and what are replications of models. Well, both actually are real physical real world systems. And a simulation is a physical system that implements a computational model. What is implementation? Well, implementation means the system somehow mirrors the mathematical structure. The physical states of the systems perform or evolve analogously to the mathematical states of the mathematical structure and how they evolve over time. A replication, on the other hand, is not only an implementation of the mathematical structure, but it also consists of the entities that the model talks about. For example, in the case of the Lotka-Volterra model, any replication of that model would have to consist of actual foxes and actual rabbits. Here we have a different model. This is a cellular automaton model of the spread of a forest fire. We can model forest fires by using a mathematical structure that is called a cellular automaton, where we basically arrange numbers in cells and see how they evolve. For example, like you can see here on the right, we can use that cellular automaton to watch the spread or to predict the spread of a forest fire. Now that's our model. And we can simulate this model. As we've done here on the right-hand side, this actually is a simulation I carried out on my laptop just a couple of days ago. And it is a simulation of the forest fire model because the pixels here on the screen behave analogous to the cellular automaton, behave analogous to the mathematical structure. They're not just random, they evolve just as the mathematical structure describes, and therefore this is a simulation. However, it's obviously not a replication. The bits and cells of my computer are most certainly not the kind of entities that the model is about. Well, what kind of entities is the model about? It's about trees, about burning trees, about healthy trees, and about the forest floor here in between. That's what the model talks about. That's the interpretation of the model. So if we want the replication of such a model, it would most certainly have to consist of healthy trees, burning trees, and some area in between. As an example, as an admittedly abstract example, think of tree saplings, which we arrange in a certain way according to the cells of our mathematical structure. Then we burn one of those tree saplings and watch how the fire spreads. This actually would be a replication of the forest fire model because it implements the cellular automaton. It consists of the kinds of entities that a model is about, and it also uses the same mechanisms. That means hot trees setting neighboring tree, or burning trees setting neighboring trees alight. So this is a proper replication. And that now becomes important when we think of brain models and neuromorphic hardware. Why is that important? Well, I want to argue that replications share more properties of the original target phenomenon than mere simulations. Example, think of the forest fire. We want to model a forest fire in northern Brandenburg, and that particular forest fire has certain features, has certain properties. One of them is, it is implementing the cellular automaton. It is modeled by the model in some sense. But that forest fire also is heating up the environment, is burning down trees and houses, and it has some heating properties. It also is lowering the ambient temperature in the surrounding forest where the trees still are healthy and intact. That's another property forests have. They lower the ambient temperature. And it has another property which is being located in Brandenburg. Now let's see how many properties simulations and replications share with those real forest fires. First, the simulation, actually it shares almost no property with the actual phenomenon. The only property it shares is implementing the mathematical structure. That is what makes it a simulation of the forest fire. But other than that, almost no properties of the real forest fire are present in the simulation. The process on my computer is not heating up the environment at the fire front, and is not cooling down the environment at the healthy tree area. None of those properties is present. That's different for replications. For replications, again, think of the tree saplings arranged in a certain way. If they are burning, they actually are heating up the environment. So they have the heating property. And actual trees, real trees, lower the ambient temperature. So the sapling replication also is lowering the ambient temperature. And it shares quite some features, quite some properties with the real forest fire. So now let's turn to neuromorphic hardware and brain models. Neuromorphic hardware consists of artificial neurons and artificial synapses. So at least in some way it is arguably made up of the kind of entities that the brain model tries to talk about, which is neurons and synapses. And it also uses the same mechanisms as the human brain. A couple of neuromorphic chips, or some neuromorphic chips, use what is called STDP learning, that is spike timing dependent plasticity learning. That is the learning mechanism which the brain also uses. and it's like restructuring the physical structure of the system by adapting the synaptic strength between the neurons upon receiving a certain stimulus. So real brains rearrange their physical structure, so do some neuromorphic chips. They really rearrange their physical makeup upon receiving a learning stimulus. Very unlike what digital computers do. Also, neuromorphic chips use temporal neuronal processing, that is, there are actual spikes in the hardware as there are actual spikes in the brain. Also, they are designed for low power consumption and real-time processing, what makes neuromorphic chips particularly suited for advanced AI technologies. And now I want to present the argument. Premise 1. Replications share more properties with the target phenomenon than simulations. That's what I try to argue for. The replication of a forest fire shares more properties with a real forest fire than the mere simulation. Premise 2. Brains have mental properties. I have certain desires and beliefs and emotions and whatnot, and we know them to be located in the brain. That leads me to the first conclusion, which is that replications of brain models are more likely than simulations to have mental properties, to be conscious. And now premise 3. Neuromorphic chips are getting closer to being replications of the brain, of brain models. That's what I also wanted to argue for. They consist of neurons and synapses, and they use the same mechanisms as the brain, and therefore at least go towards being replications of brain models. And this leads me to my final conclusion. Neuromorphic chips are more likely than standard digital hardware to generate artificial consciousness. This is the claim I wanted to make. And what we learned from that is that I think we should take a closer look at advanced neuromorphic systems and observe whether they might or might not develop artificial consciousness. That's from my side. Thank you very much for your attention, and I'm looking forward to answering some of your questions. Thank you.